Transportation models are just one of the specialized linear programming models. We now have two other specialized linear programming models. We have transshipment and assignment models. Let's begin with transshipment. The transshipment problem is sometimes called the minimum cost network flow problem. It is the most general of the linear network models and contains transportation and assignment models as special cases. Its solution methodology is similar to the transportation modified distribution method. The transshipment model differs from the transportation model in that it allows nodes or points that are neither pure origins nor pure destinations, meaning there would be nodes in the network diagram or in your transshipment model that are considered as conduits, not exactly final destinations nor pure origins. The origins and destinations of a transportation problem are sources and sinks respectively. Source nodes can be thought of as having supply available, while sink nodes typically represent demand points. Transshipment models allow the presence of a transshipment point, or your conduits, that has arcs leading into and out of the node. Transshipment nodes can have a supply or demand. They can also have a supply or demand of zero. Let me elaborate on the last sentence. Again, transshipment nodes can have a supply or demand. For example, your typical manufacturing type of company wherein the products are manufactured or finished in the processing plant, and then the finished products would then have to be transferred to the warehouses, and then depending on the demand from the outlets or the branches of the company, then the branches would have to draw their supply from the warehouses. In that particular setup, your warehouses would be your transshipment point, or in a network diagram, that would be a transshipment node. And in that instance, your warehouses have supply as soon as they receive finished products from the processing plant. Therefore, they would have inventory. And then such a supply that they keep would then be transferred to the branches or to the outlets depending on the demand from the outlets. So in that instance, your warehouses have supply. And then if ever the supply or the inventory in the warehouses would go below a particular threshold, then they can demand from the processing plants to produce more and deliver more finished products to them. So again, in that entire process, the warehouses would be your transshipment nodes, and such transshipment nodes have both supply and demand. Now, the second half of that sentence also says that transshipment nodes can also have a supply or demand of zero. For example, if let's say you sell something online, let's say you sell your specialized design of a particular notebook, and then you posted your product on an online shopping network or platform, and then you got a buyer from London. What would you do with your notebook? Most likely, you are going to have your notebook shipped to your buyer in London using one of the courier services available. You have your DHL, your Federal Express, your To Go, and so on. Okay? So what you're going to do is you go to, let's say, your DHL, and then DHL would then be the one to deliver your notebook to your buyer in London. In that particular instance, DHL or your courier service is your transshipment node. Now, in that instance as well, can we say that DHL has supply or demand? In that instance, we cannot. Why? Because can DHL demand that you send something abroad? No, they are merely waiting for customers to approach them. So they cannot demand from customers to send something. Can DHL say that, let's say, once they receive your notebook, such item is already considered as their supply? Again, no. Because if ever DHL would lose your notebook in transit going to London, then depending on actually your design, let's say you have your own DNA in that particular design, most likely they would not be able to replicate such product if they lose it. Therefore, they cannot assume that your notebook that you have given to them is considered as their supply. Still, DHL is considered as a transshipment node. So that is why transshipment nodes can have a supply or demand, but they can also have a supply or demand of 0. Following now is a general transshipment model, beginning with your decision variables. So in the transshipment model, the capital letter N represents the set of all arcs in the network, or the set of all possible routes from one node to another node, including the transshipment nodes or your conduits. Then you have the small letter n, which represents the number of nodes in the network. This would be the number of your sources of your supply, the number of your conduits, and then the number of your final destination points. Followed by x sub I sub j, which represents the amount of flow from node I to node j, or the amount of units of supply transferring from one node to another node. Then you have C sub I sub j, which represents the per unit cost of flow from node I to node j, which is the cost of shipping or transferring goods from one point to another point. Now what's new in this model would be the next variables. You have your L sub I sub j, which represents the lower bound on flow from node I to node j. And then you have U sub I sub j, which represents the upper bound on flow from node I to node j. L sub I sub j, which is the lower bound. Let's say you are an owner of a shipping company which provides cargo shipping services. And each of your ship can accommodate up to 10 tons of cargo. Would you allow one of your ships to go to London if it is only carrying one notebook? Of course, that would not be economical nor profitable for you. Therefore, there should be a lower bound or a minimum cargo that you would accept before your ship would go to wherever it's supposed to go. Then you have your U sub I sub j, which is the upper bound. Since we are dealing here with vessels, then we know that each vessel has a maximum capacity. And if your cargo is in excess of the maximum capacity of a particular ship, technically you are not supposed to allow that ship to go out to sea because it would be very dangerous and very risky. So that is the L sub I sub j and the U sub I sub j. Then you have B sub j, which represents the supply or demand at a particular node or node j. So it depends on what node you are referring to, whether the node is a supplier, a conduit, or a demand or destination point. Following now is a general transshipment model wherein our objective is to minimize total transshipment cost, which is the sum of the cost of shipping from one node to another node and the amount to be shipped from one node to another node. Subject to the general equation would be total flow out minus total flow in is equal to the node supply or demand, which is represented mathematically in the next row. And then the last row would be the fact that your shipping pattern should comply with the lower and upper bounds of each route. Let's look at a transshipment scenario. This is the typical network diagram that you're going to see if you're dealing with a transshipment scenario. Nodes 1 and 2 are your supply sites or your sources of your supply. They are known as your supply sites or sources because there are values beside the nodes that are positive in form. they represent the actual supply values of those nodes or those sites. Nodes 3 and 4 are your distribution centers or your transshipment points. They are your conduits. If there is a positive value in your transshipment points, then that means your transshipment points have supply. So you are dealing with the warehouse type of scenario. But in this case, since there are no values in the perimeter of your transshipment points, then we are dealing with your online selling or your DHL scenario. That means nodes 3 and 4 do not have supply nor demand. They are just conduits. Then you have nodes 5, 6, and 7, which are your demand sites or your sinks. You know that they are your demand sites or your sinks because there are negative values beside them. Demand values are placed in the form of a negative. Now, along each arc connecting the nodes, you have values inside boxes. The values inside boxes along arcs connecting the nodes represent cost of shipping from one node to another node. And then you also have an ordered pair of numbers on each arc connecting the two nodes. The first value in that ordered pair of numbers would be your lower bound, and the second value would be your upper bound. If you would notice, for example, in arc 1 going to 3, in the ordered pair of numbers shown there, the upper bound is infinity. How can infinity happen? Usually, shipping companies are parts of an organization or an association among shipping providers or shipping service providers. So if ever they would exceed their maximum capacity, they can pass some of the cargo to another provider, so long as they inform their customer that they are going to do such thing. Okay? Although in reality, sometimes they don't, but that is not the ethical thing to do. The ethical thing to do is for the shipping company to inform their customer that they would have to pass some of their cargo to another provider because they are already in excess of their capacity. That is why infinity can happen. Okay? So how do we now represent this particular transshipment scenario in network diagram form, or in mathematical model form? Let's begin with your objective function equation. So again, your objective function is to minimize total transshipment point. So our definition would be let x sub I sub j represent the amount to be shipped from source I to destination j. The difference between the way you define your decision variables in transshipment versus your regular transportation model is in the definition of your I and your j. In transshipment, particularly in this example, I is 1, 2, 3, and 4, representing the nodes 1, 2, 3, and 4, while j is equal to 3, 4, 5, 6, and 7. If you would notice, there is an overlap. The overlap would be your conduits or your distribution centers or transshipment points, which are nodes 3 and 4. They are both present in I and j. That means in the first leg of the shipping route, nodes 3 and 4 are destinations, while in the second leg, nodes 3 and 4 are already your sources of your supply. After you have defined your decision variables, then we now proceed to your objective function equation, which I said earlier is to minimize total transshipment cost. So again, the values inside the boxes along the arc connecting the nodes represent cost of shipping. So if you focus on those values inside the boxes, your objective function equation would be mean z is equal to 5 x sub 1, 3 plus 2 x sub 1, 4 plus 8 x sub 2, 4 plus 8 again x sub 3, 5 plus 6 x sub 3, 6 plus 10 x sub 4, 5 plus 7 x sub 4, 6 plus 2 x sub 4, 7. Then we proceed to your constraints under the heading Subject 2. The first set of constraints would be in terms of the lower and upper bounds of each root. So if we look at the lower and upper bounds of each root, then we have the following equations. For root x sub 1, 3, it would be greater than or equal to 0 because the minimum is 0 and then the upper bound is infinity. For root x sub 1, 4, it would be less than or equal to 20, which is the upper bound, but greater than or equal to 8, which is the lower bound. For root x sub 2, 4, it would again be greater than or equal to 0 based on the lower and upper bounds of that root. Moving now to root x sub 3, 5. It would be less than or equal to 15, but greater than or equal to 0. For root x sub 3, 6, you have x sub 3, 6 is greater than or equal to 5. For root x sub 4, 5, that would be less than or equal to 15, but greater than or equal to 0. For root x sub 4, 6, that would be greater than or equal to 0. And for root x sub 4, 7, that would be less than or equal to 20, but greater than or equal to 10. So those are the equations that refer to the lower and upper bound values along each arc in each root. Then, we also have the general equation wherein total flow out minus total flow in is equal to the node supply or demand. Let's begin with node 1. If you would look at the arrows connected to node 1, you have two flow outs. That is, one going to 3 and one going to 4. And you don't have any flow ins. There's no arrow or arrowhead connected to node 1. Therefore, you only have flow outs. So following the formula total flow out minus total flow in is equal to the node supply or demand, then we would get the equation x sub 1, 3 plus x sub 1, 4 representing the two flow outs equal to 29, which represents the supply at node 1. Next, focusing now on node 2. For node 2, you only have one flow out, which is going to node 4. Therefore, again, following the equation total flow out minus total flow in equal to the node supply or demand, then you would have x sub 2, 4 is equal to 36. 36 being the supply of node 2. Next, we focus on node 3. For node 3, you have two flow outs, namely those going to node 5 and the other one going to node 6, while you have one flow in, which is coming from node 1, based on the arrowhead connected to node 3. So following again the equation total flow out minus total flow in is equal to the node supply or demand, let's begin with total flow out. You have x sub 3, 5 plus x sub 3, 6. And then we subtract the flow in, which is your x sub 1, 3. And then since there is no supply or demand value in the perimeter of node 3, then your right hand side constant is equal to 0. Considering that we said that this scenario is your DHL scenario, which is where your nodes 3 and 4 are merely conduits. Following the same pattern for node 4 this time, you have three flow outs going to node 5, 6, and 7, and you have two flow ins coming from node 1 and node 2. So again, based on the pattern total flow out minus total flow in is equal to node supply or demand, then the resulting equation would be x sub 4, 5 plus x sub 4, 6 plus x sub 4, 7 minus x sub 1, 4 minus x sub 2, 4 is equal to 0. Then we go to node 5. For node 5, there is no flow out, but you have two flow ins coming from nodes 3 and 4. So again, following the formula total flow out minus total flow in equal to the node supply and demand, and since there is no flow out, then we begin with minus. So minus x sub 3, 5 minus x sub 4, 5, representing the two flow ins, equal to the demand at node 5, which is your negative 20. Next, we now go to your node 6. Again, there are no flow outs, only flow ins. So the equation that we can come up for node 6 would be x sub minus x sub 36 minus x sub 46 is equal to negative 28. And then for node 7, there's only one flow in, so you have minus x sub 47 equal to negative 17. The last three equations are not in standard form, considering that on our very first lecture day, we said that all of your equations is where you should have the right-hand side values to be in positive form. And since we have here negative right-hand side constants in the last three equations, then we have to multiply each of those three equations by negative 1 to make the right-hand side constants positive before we proceed with your solution methodology, which can be either using your simplex method or using your transportation method. But in your transportation method, you would have to do it in parts depending on the leg of the shipping destination. So the first leg would be transferring supply from nodes 1 and 2 to nodes 3 and 4. Once you are done with that, then you proceed to the next leg, which is transferring the supplies available in 3 and 4 going to nodes 5, 6, and 7. But this is how you come up with your mathematical model in a transshipment type of scenario. Again, for transshipment, you just have to remember that the equation you have to follow is total flow out minus total flow in is equal to the node supply or demand. Other than that, you also have your lower and upper bounds to contend with, and that would constitute your entire constraint equations. Moving now to the next specialized linear programming model, which is your assignment model. The assignment model is a special case of the transportation problem wherein the basic idea is to assign n single elements rather than many units from each source to destination. What does that mean? It can be described as a transportation model with an equal number of sources and destinations with all supply and demand values equal to 1, meaning each supplier can only supply one unit and each demand point can only demand one unit as well. Unlike your usual transportation problem, wherein your suppliers can have multiple supply values and your demand points can also have multiple demand values, in the assignment model, each supplier can only have a supply of one unit, and each demand point can also have only a demand of one unit. And since there is an equal number of sources and destinations, then you would always have a square tableau. Typical applications of the assignment model include the least cost or least time assignment of jobs to machines, workers to tasks, salespersons to territories, and contracts to contractors. So in general, if there are n agents to be assigned to n tasks, the assignment model is stated as follows. Minimize total cost, subject to, again, typical of a transportation problem, the first set of equations would be referring to your supply, wherein each supplier this time would only have a supply value of 1. The second set of equations would refer to your demand, wherein each demand point would have only a demand of 1 unit. And then you have your non-negativity constraint equation to ensure that you don't have an assignment of a negative value. For example, let's say you are the head of human resources of a multinational company. And then you got a request for a secretary each from 3 vice presidents. One is located in London, another is in New York, another is in Shanghai. So each vice president is demanding for one secretary. So their demand would all be equal to 1. And you happen to have 3 available secretaries. Secretary 1 can be sourced from India. Secretary 2 can be sourced from Nigeria. Secretary 3 can be sourced from Dominican Republic, just for example. So each secretary represents a supply of 1 unit. Okay? So this type of model is very easy because you only have supply values of 1 and demand values of 1. Okay? The challenge when applying the assignment model is in determining the cost values placed in the small cells, small squares, or small rectangles. For example, how much would it cost you as a company to send the secretary coming from India to, let's say, the vice president in Shanghai? How much would it cost you to train that secretary to speak Mandarin? How much would it cost you to transport that secretary, including her or his entire family, and transplant them to Shanghai, and so on? Similar to secretary number 2, the one coming from, what did I say earlier? Or secretary number 3 from the Dominican Republic. How much would it cost you to send that person to London? Okay, learning how to speak English fluently, and so on. Okay, so again, the challenge in the assignment model is determining the cost of assignment placed inside the small cells, small squares, or small rectangles. Similarly, if let's say your scenario is where you have several machinery and you are choosing which laborer would have to be assigned to operate a particular machinery, then those costs would most likely include costs of training a particular laborer to operate a machinery, even certification requirements, for example, or unlearning a previous skill and determining the potential of that particular labor for more skills, particularly if such machinery is something that gets upgraded every now and so on. So again, just to be clear, this particular type of specialized linear programming model is easy because you only have supply values and demand values equal to 1. The challenge is in determining the cost values that you place inside the small cells, small squares, or small rectangles. Once you have determined those values, then just apply your preferred heuristic and your preferred optimization technique under the transportation modeling, and you would be able to come up with your preferred or optimal or ideal assignment of a particular supply to a particular demand point.